सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello, everybody. Hope you are all having a wonderful day so far. My name is Arjuna, and today I'll be hosting our national webinar organized by Maths Aspirants. Actually, I am a little bit intimidated by the big people around here. We have such great personalities in today's event. Our speaker, Dr. 𝕗𝕚𝕚𝕚𝕚 sir, Associate Professor of IIT Gandhinagar, and we have our beloved Vinod Kumar sir, Emeritus Professor, CUSAT, and also Vice President of Ramanujan Mathematical Society. And let me start with Maths Aspirants. Let me just talk a little about Maths Aspirants. It was all started in 2017 when Dr. Vinod Kumar sir thought about starting a Maths community which can discuss some problems, solutions, and can you believe that it was just a Maths WhatsApp group? And now this informal Maths community has a global impact. When we are conducting some national webinars, we are getting registration from different parts of the world, not only from different places of India. So it's a big growth. It's really a huge growth. I am not telling a lot because I know people here are going to tell a lot about Maths Aspirants, but it is a great platform for all the Maths lovers because it has online Google Form test series, national webinars, talks, and problem-solving sessions. And recently, we had JAM exam preparations, and the result was wonderful. So this community is growing. And let me just tell all those names of national webinars we had so far. You all know this is the 8th national webinar, and it is on the topic An Introduction to the Theory of Partitions. So last successful national webinar was on December 22nd, and it was a couple of gems from Ramanujan's garden. Before that, we had Building a Successful Career with Mathematics Degree, Opportunities and Challenges in August. And we had Mathematics for Democracy in December 2021, Glimpses of Ancient Indian Mathematics on November 2021, Beauty of Complex Analysis in August 2021, which was by Dr. Bijumon Kumar sir. That's a beautiful thing, and because he's here today with us. And before that, we had Artificial Intelligence, Myths and Realities on November 2020, and the very first national webinar by Maths Aspirants community was held in August 2020 on our Independence Day. So I'm really happy that I could host many of these national webinars, including the very first webinar. I consider it as an honor, and I have to say a big thank you to Vinod Kumar sir, Bijumon sir, who is working behind the curtain for all the technical stuff, and all the people in organizing team, teachers, students, and all other well-wishers associated to Maths Aspirant Group. Okay, so coming back to this national webinar is actually the first national webinar Maths Aspirants is organizing in 2023. So I hope this would be a great start. And yes, a wonderful, wonderful event is going to be here. And we have Dr. 𝕗𝕚𝕚𝕚𝕚 sir, Associate Professor, Indian Institute of Technology, Gandhinagar. He was awarded the Swarna Jayanti Fellowship, prestigious fellowship, and also is a member of International Young Academy of Sciences. It's really a great pleasure to have you, sir. First of all, let me welcome on behalf of everyone who is here, on behalf of Maths Aspirants, with great respect and love. Welcome, Dr. Atul Dikshit, sir, to the event. Okay, and next, I would like to welcome our beloved, our dearest, our man of guidance, Dr. Bijumon Kumar sir. He's emeritus professor in CUSAT and also vice president of Ramanujan Mathematical Society. It's our extreme pleasure to have him here for the introductory talk for Atul Dikshit sir. Welcome, Bijumon Kumar sir. I'd like to extend my welcome to Dr. Vinod Kumar sir, who is the pillar of the Maths Aspirants community. If I start to talk about him, there is a lot to talk, and I don't want to take that much time today because we need to start. And our beloved Dr. Bijumon sir, and we have our organizing team, Jia, Anne-Marie, Kajal, and Unnadi. And also we have Gayatri. So this is the organizing team for today. I welcome everybody with lots of love, and I hope this program is going to be a success like all the programs we had. And now I like to welcome all the participants who is patiently hearing everything. And I hope you will all have a wonderful experience today on this Pi Day, right? And yes, Pi Day is the special thing about today, and we know the people around the world who is connected with mathematics celebrating Pi Day, and on this Pi Day, this event is making it more beautiful, more wonderful. So welcoming all of you, let me start the program officially. First, I would like to call our Vinod sir to share a few words with us.
Good evening, friends. Pi Day greetings to all. As a part of the webinar series, Math Ecstasy, an online odyssey through mathematics, initiated by Maths Aspirants Groups, today we have the 8th national webinar on the topic Theory of Partitions. We are all blessed to have a most apt resource person for today's webinar, Dr. Atul Dikshit, Associate Professor of Mathematics, IIT Gandhinagar. I would like to express my sincere thanks and gratitude to him for accepting our invitation and joining with us on this auspicious Pi Day evening. I am indebted to Professor Ampat Vijay Kumar, Emeritus Professor, Cochin University of Science and Technology, for helping me to connect with Dr. Atul and also for the enormous helps and support throughout my journey with Math Aspirants Groups. On this occasion, I fondly remember all my teachers, friends, and well-wishers. I extend my heartfelt thanks to all members of the organizing team. Wish you all a great academic time ahead. Thank you.
Now, I would like to invite Dr. Bijumon Kumar sir for giving us an introduction for our wonderful speaker. And I know he is the best person to do that. Bijumon Kumar sir.
Welcome to this national webinar organized by the Math Aspirants Groups based at Kerala. Today we have a speaker, Atul Dikshit from IIT Gandhinagar, who is basically a Bachelor of Engineering in Computer Engineering from University of Mumbai and moved to Texas Technical University for MS Mathematics and finally to University of Illinois at Urbana-Champaign, USA for doing his PhD during 2006 to 2012 under the guidance of a great number theorist, very renowned, celebrated number theorist, Bruce Berndt. He has wonderful list of publications, mostly jointly with Bruce Berndt. And he's an expert in analytical number theory, theory of partitions, modular forms, special functions, and so on. He has more than 60 papers to his credit, and he has been honored with the Swarna Jayanti Fellowship of Department of Science and Technology and Gabor Sigo Prize from SIAM, Society for Industrial and Applied Mathematics, USA 2021. I met him for the first time a couple of months back at MIT Manipal, and I immediately talked to Vinod, saying that I could nab a person who could talk to you all during a very special day. So I'm extremely happy that Atul accepted our invitation, and he is going to talk on theory of partitions. Before I conclude, those who have not been to a museum in Chennai, Ramanujan Museum is there, and you will see several contributions, several display boards about the contributions of Srinivasa Ramanujan about pi. And the last, at the exit, you will say there's a very good quote: "Never say never again. Pi is equal to 22/7." I repeat, never say never again. Pi is equal to 22/7. So pi is not equal to 22/7. That Atul will repeatedly talk, and is going to talk on one of the very beautiful area of number theory of partitions. And I welcome, on behalf of the Math Aspirants Group, Atul to this webinar. Over to Atul.
Thank you all. Good evening, everyone. So thank you, Ajuna, for introducing me, and thank you, Professor Vinod Kumar and Professor Vijay Kumar Ambat, for this kind introduction. It's my pleasure and honor to give a talk in this Math Aspirants Group. The topic that I have selected for today's lecture is theory of partitions, which is something which even someone who is not initiated into this theory will be able to grasp most out of it. So I'll be giving an introduction to this beautiful area of mathematics, in particular in number theory, which has connections with incredibly many areas of mathematics outside of number theory as well. Why is that so? It's because of the very definition of partition. What is a partition of a positive integer n? It's a finite, non-increasing sequence of positive integers which sum to n. So let's take an example. I'm taking n equal to 5. How many partitions of 5 there are? So I have listed down these partitions. So you can write 5 as 5 itself, or you can write it as 4 plus 1. Now I'm using this canonical way of writing a partition, which means the largest part will come first, then the next largest, and so on. And another thing is, the order of the summands will not matter. So, for example, here 3 plus 1 plus 1 is the same partition as 1 plus 3 plus 1 is the same partition as 1 plus 1 plus 3. Okay, so the order doesn't matter. So once I write it in the canonical form, then all these three different ways of writing 3 plus 1 plus 1 is the same. And I'll write it as 3 plus 1 plus 1. So then you have 2 1s plus 1, 2 plus 3 1s, and then 5 1s. So there are 7 ways to write 5. Now this is something so very fundamental in mathematics, right? The basic addition of numbers in order to get a particular number. So it ought to be useful in various different areas of mathematics, and we'll see a flavor of some areas where this turns up. So let me denote a function p of n which counts the number of partitions of n. So for example, we have seen when n is equal to 5, there are 7 partitions of 5. So p of 5 is equal to 7. As simple as that. Now, there are many questions that come up into our mind once we see a certain function. What are the basic questions that come to our mind? What happens to p of n as n grows larger and larger? That's a very basic question, right? So let me try to answer this by means of a scene from the movie The Man Who Knew Infinity, which was a movie that was made in 2016 on the life of Ramanujan. So this is not how exactly this happened, but it's just some kind of imagination, but I think you will like it. So you will see Dev Patel as Ramanujan sailing to England, and he is of course dejected because he has to leave his family back in India to go to England to work with G.H. Hardy. And so you can see him disappointed. There is a fellow Indian who unnecessarily provokes him, saying, England is 6,000 miles. Can you imagine? And Ramanujan bluntly replies, I have known larger numbers. Larger numbers than 6,000. Now one can actually guess what he's trying to think about, because if I look at, I think he's talking about the values of P of n, because P of n grows very quickly. So let's look at some values. P of 1 is 1. P of 2 is 2, because 2 can be written as 2, 1 plus 1. P of 4 we have, one can actually write down 5 different ways. P of 5 we know is 7. But very soon, P of 50 is this, how many digits you have? 6-digit number, 2,04,226 partitions. P of 100 is this 9-digit number. So it looks like they grow very fast. So that's what Ramanujan is telling. I have known larger numbers. And we know that Ramanujan was extremely good at computing large numbers, doing all sort of multiplication, addition, very fast. There is another scene where Ramanujan is shown to interact with Major McMahon, who was a very famous combinatorialist at University of Cambridge. So again, let me just say that this is not how it happened actually in the life of Ramanujan, but this is a very good scene in the movie. In the movie, it is shown that McMahon is not really convinced of Hardy and Ramanujan's way of calculating P of n for large values of n. He is of the opinion that partitions have to be calculated by hand. So even if it is P of 50, which is 2,04,226, you have to calculate all by hand. That's how you will get the answer. Whereas Ramanujan and Hardy were of the opinion that one can get a formula. If you put n in there, the formula should give you the value of the partition, value of P of n for whichever n you have. So this was, in the movie, it is shown that this kind of difference exists between these two teams. And so in reality, what happened was Hardy and Ramanujan had a formula and they wanted to check through some other means. And McMahon was another mathematician who was extremely fast with calculations. And so Hardy and Ramanujan suggested that we will ask McMahon to prepare a list of P of n from n going from 1 to 200. Now the formula of Hardy and Ramanujan, you will see very soon, is such that it gives you better and better answer as your n grows larger and larger. So that's why they told him to calculate up to 200. 200 is, you see, P of 100 itself is this 9-digit number. So P of 200 will be very large, right? So they were of the opinion that, okay, one can get probably a close enough answer from our formula versus his calculation. That was the idea. So in the movie, it is shown after they come back in a month, then McMahon asks Ramanujan, what has your formula given you? And here is what the two numbers, one through McMahon, one through Ramanujan. Now, in the movie, they have made one error, which is a very blatant error, but you cannot view it unless you zoom it. There is a 9, there is an 8. It should be 9. So you see that the only difference would be in the decimal portion, which is truncated here. But P of n is an integer, so one can truncate the decimal part and one will get the integer value which matches perfectly. Of course, you have to take this as 9 and then they match perfectly. So then McMahon is completely aghast and he sees how in the world you calculated this. And that was through this formula, which I told you that once n becomes larger and larger, P of n approaches this number. And this also explains why that number was growing very fast, because you see this exponential growth, almost exponential growth. Okay, so what is this tilde meaning? It is telling that if I take the quotient P of n over this number, as n tends to infinity, this quotient will become 1. Okay, so in infinity, they match. So for larger and larger values of n, they will be very, very close. And the right-hand side will of course not necessarily be an integer always, and or in most cases it will not be an integer, but the left hand side is. So because they are matching, you just truncate off the decimal portion and you'll get the integer. So that's what Hardy and Ramanujan did. Now there are many different ways of working
Excuse
in
me,
partition.
sir.
Yes.
Could you make the screen into the full screen mode?
Okay, sure. Is it better? Yeah. Is it full screen now?
Not exactly, I think.
Oh, okay. Let me see. Oh, okay. Yeah. Okay. So there are many different ways of working in partition theory. You can do this analytic theory of partitions. So you can apply analysis and methods from number theory to work on partitions. Or you can actually use combinatorial ways to get more and more information about partitions. And combinatorics is mathematics of counting. And whenever you have counting, there is a very important construct in mathematics, which I'm sure everybody is aware of. It's called as generating function. Now, a famous mathematician, Herbert Wilf, once said that a generating function is a clothesline. A generating function of a sequence is a clothesline on which you hang all elements of the sequence. So imagine you have a cupboard in your home, and that cupboard has a rod on which you hang clothes through hangers, right? Now, if I want to take all these clothes from one room to another, from one cupboard in one room to another cupboard in another room, will I be doing one by one, taking the one hanger and then putting the cloth from one end of one cupboard to another? No, I can actually take the whole iron rod itself and put it from here to there. That's what exactly generating function of a sequence does. It gives you information about a sequence all at once. And most of the times, it's something which you can also analyze by means of, say, complex analysis or other methods in analysis. So generating function is something really very useful. So the next question that comes to our mind is P of n is a sequence, right? As n goes from 1, 2, 3, 4, so on, P of 1, P of 2, P of 3, P of 4, this is a sequence. So what is the generating function of P of n? So as is true with many branches of mathematics, it is said that theory of partitions mainly gained momentum, or one can even say that theory of partitions started with Euler. In 18th century, Euler showed the generating function of partitions, which I'm writing as P of n q to the n summation n equal to 0 to infinity. So it is an infinite series, P of 0 times q to the 0 plus P of 1 times q to the 1 plus P of 2 q square plus so on, is given by this infinite product. Now on one side you have infinite series, on the other side you have infinite product. Now one thing is, if I have to analyze this through analysis, then of course once I see infinite series or infinite products, I have to be cautious enough to see when they converge. Okay, if I'm only looking at combinatorial properties, then convergence can be convergence takes a back seat. But for analysis, of course, I have to see when all these things converge. Okay, but today I'm not going to really go into that rigorous proof of how to make these infinite products. One can actually, of course, see this in any basic complex analysis book. And when does infinite product converges, or when does infinite series converges? All that one can actually see. So as long as mod q is less than 1, so q is a complex number sitting inside the unit disk, these things converge. Okay, so this will be the assumption almost all of the times. So how do we get second equality? So let us start from that infinite product. Because mod q is less than 1, I can write 1 upon 1 minus q as summation n1 equal to 0 to infinity q to the power n1, right? The basic geometric series. 1 upon 1 minus q square as summation n2 going from 0 to infinity, q square to the power n2, then q cube to the power n3, and dot dot dot. This doesn't end here. It's an infinite product. Okay, I have just written each one of these expressions as an infinite series, and I have multiplied all of them. Okay, so let me go ahead with this and say that I have not a double sum or a triple sum or a quadruple sum, but an infinite fold sum, because you have infinitely many indices of summation, n1, n2, n3, so on, all going from 0 to infinity, q to the power 1 times n1 plus 2 times n2 plus 3 times n3 plus dot dot dot. Okay. Now, suppose I let this exponent here be equal to n. What is the first thing that comes to our mind? Well, n is a finite thing. So on the left hand side also I have to have a finite thing. n1, n2, n3, n4, all of them go from 0 to infinity. So if I have to have the left hand side to be finite, from certain point onwards, from certain I onwards, all of the ni's, ni plus 1, ni plus 2, all of them must be 0. Otherwise, it will be an infinite sum, right? And that cannot equal this finite number n. So once I know this, then the other thing is, how do I make sense of these numbers, n1, n2, n3, those which are non-zero? Okay, I mean the previous ones. So n1, n2, so on up to ni minus 1. So here is one way. So what, in other words, I'm trying to do is, if I let this be equal to n, then what is the coefficient of q to the power n in the expansion of this particular product is what I'm trying to get at. And what I'll prove to you is that that coefficient must be p of n. How do we get that? Let us attach a meaning to these ni's. So the meaning is this: n1 counts how many times 1 appears in a partition of n. n2 counts how many times 2 appears in a partition of n, and so on. ni in general counts how many times I appears as a part in a partition of n. Then how many times will you get q to the power n in the expansion of this as a power series? Of course, as many times as there are partitions of n. See, for example, let me explain the case when n is equal to 4. When n is equal to 4, what will be n5, n6, n7, and so on? Of course, they will be 0, because if n5 is, say, 1, then I have 5 times n5, and that plus whatever here cannot be equal to 4. Okay, so the only non-zero possible values are n1, n2, n3, n4. Okay, now that I have n1, n2, n3, n4 in hand, how many different ways can I choose those values so as to get the answer as 4? Well, I can choose n2, n3, n4 all to be 0, and then I can choose n1 to be 4, and then 1 times 4 will equal 4. But in other words, that is nothing but the partition 1 plus 1 plus 1 plus 1. Similarly, I can take n1 to be 1, n2 to be 0, n3 to be 1, and n4 to be 0. And then that will give me a partition 3 plus 1. So you see, how many solutions will I get? That will be as many as the partitions, and hence the coefficient of q to the power n is p of n. In other words, we have found out the generating function of p of n, which is this particular infinite product. Now, of what good is this infinite product is the next question. So first of all, just going by this quote of Herbert Wilf, just understand that all these p of n values, or essentially the sequence p of n, is encoded in this single expression, single infinite product. If you expand that, it not only gives you p of 0 or p of 1 or p of 2, but it gives you all at once. Okay. So now, what are the advantages of generating functions? So let me explain one thing. Let me start with a partition of all partitions of 6. There are 11 partitions of 6. You can write all of them down. Now let me put some restrictions on the parts. The first restriction that I put is I want only odd parts to appear in the partitions. So for example, I don't want this because there is an even part and an odd part. I want only partitions with odd parts. How many of them will be there? Of 6. There are 4 only. 5 plus 1, 3 plus 3, 3 plus 1 plus 1 plus 1, and then 5 ones. Sorry, 6 ones. Yeah, we are looking at partitions of 6. So there are 4 of them. Now I change my restriction and I say that I don't want any repetitions in parts. So something like this, which I took here, I'm not going to allow that. I want only distinct parts in my partition. So now how many such partitions of 6 do I have? So there are also 4 partitions into distinct parts. So no repetition. So 6 itself, or 5 plus 1, 4 plus 2, and 3 plus 2 plus 1. Is this a coincidence? Or is it something which is always true? If you want to try it for 5 or 7, 8, 9, 10, you can do that. You will always get the same answer. But don't go beyond 20 because it's a very large number. I mean, they start growing very fast. But how do we prove this? Now see, what are we really trying to do is, I have 2 sets of quantities and I want to say that their cardinalities are same. How does one address such problems in mathematics? Maybe you create a bijection from one set to another, or else another way is to use generating functions, which is what I'm going to show you. Okay, so this is actually a theorem of Euler, that the number of partitions of n into odd parts always equals the number of partitions of n into distinct parts. Okay, so how does one prove? So I'm going to denote by A of n the number of partitions of n into odd parts, and by B of n the number of partitions of n into distinct parts. So what do I have to show? I have to show that A of n is equal to B of n. This is equivalent to showing that their generating functions are the same, because the linear independence of the monomials 1, q, q square, q cube, so on, will tell me that, okay, if this is true, then of course A of n is equal to B of n for all n's, all at once. Okay, so if that is the case, the next question that I have is to find out an expression for this, find out an expression for this, and then try to show that they are equal. So let's start with the first one. Here I'm only allowing parts to be odd. Now, in the P of n case, what did you have here in the denominator? You had 1 minus q, 1 minus q square, 1 minus q cube, 1 minus q raised to 4, all of them. But I'm taking here only 1 minus q, 1 minus q cube, 1 minus q to the 5, 1 minus q to the 7, and so on. Why? Because I want the parts to be only odd. I'm not allowing even parts. As simple as that. What about this other one? I don't want any repetitions. So see, if I go back, or maybe I have here itself, let me explain why the generating function of this B of n turns out to be this particular infinite product. So here is the simple argument. Let us consider m to be a part of my partition, which is enumerated by B of n. So I will have 1 upon 1 minus q to the power m, and it has this geometric series expansion. Now what is the meaning? This 0 tells me that m does not appear if I'm choosing this particular one. Or if I'm choosing this particular one, it tells me that m appears only once, or m appears twice, or m appears 3 times, and so on. Now what am I interested in? Partitions into distinct parts. Distinct parts means those which do not repeat. Those which do not repeat means either they do not appear, or if they appear only once. So I will discard this particular thing, because this is telling me that m is repeating twice or thrice or so on. I only want to take this and this for a particular m. So what is this? 1 plus q to the power m. Now m can be any of these parts. So I have 1 plus q times 1 plus q square times 1 plus q cube, and so on. Now that I have identified the right hand sides of 2 and 3, I want to show them to be equal. How do we do that? It's a very simple logic, but to make it rigorous, you will have to actually use complex analysis, the theory of infinite products and all, which I'm not going to go into. But just take this left hand side. put in the missing factors, as in multiply top and bottom by 1 minus q square, then by 1 minus q to the 4, then by 1 minus q to the 6, and so on. And now just look at 1 minus q square upon 1 minus q, that is 1 plus q. 1 minus q raised to 4 upon 1 minus q square, that is 1 plus q square. Just using a square minus b square is a minus b times a plus b. That gives you the right hand side. And that proves Euler's theorem all at once, that whenever you take the number of partitions of n into odd parts, that number will be the same as the number of partitions of n into distinct parts. There are many further refinements of this result. Even now, people find refinements, but of course, I'm not going to go into this. I just wanted to show applicability of generating functions in proving simple partition theorems. Not just simple partition theorems, but also many complex partition results can be proved this way. Now, what is the rigor that I was saying I'm not going to talk about is this particular thing. If I had only finite product that I'm multiplying the top and bottom, that is okay. But I'm here multiplying the infinite product, right? That has to be made rigorous. And one can actually do that by multiplying finitely many and then say, letting that capital N tend into infinity. So that requires some convergence theorems and all, but I don't want to go into that today. Okay, where are partitions useful in mathematics? So let me list some areas. Non-parametric statistics, statistical mechanics, probability and statistics, particle physics, wherein asymptotics of partition functions and related things are more into use, computer science, group theory, and many people in group theory or in algebra, they use Young tableau. And that is something very, very reminiscent of Ferrer's graph. In fact, equivalent to what people in partition theory call as Ferrer's graph. We are going to see some examples. Basic hypergeometric series, modular forms, mock modular forms. So, who were the ones with whom this beautiful area blossomed? So, Euler and Gauss, names which we cannot omit. Then further Jacobi, Sylvester, the same Sylvester from algebra or invariant theory that we know. Then came Hardy, Ramanujan. Both made very stunning advances in this field. I'm going to talk about many different contributions of Ramanujan in this talk. And George Andrews, who is the living legend in this area of partitions, and Freeman Dyson, who was a mathematician as well as a physicist. When he was 16-year-old, he wrote his first paper on partitions, and that was in 1944. And he passed away in 2020, but in 2012, he was already again publishing in partitions. So you see, from 1944 to 2012, how many years? 68 years. Anyway, so let us actually go back to this calculation of P of n from n equal to 1 to 200. So Hardy and Ramanujan had asked McMahon to calculate these values of P of n. How did McMahon calculate? I mean, it's not an easy task. Of course, he was a very fast person in calculating these things, but still, these are notoriously big numbers. So he used this recurrence, which Euler had obtained. So P of n can be given by this particular expression. So if you have calculated these values, of course, you can use them to calculate P of n. So that's what McMahon did. Then this P of n, which you have just calculated, can be used to calculate further values. Like this, he calculated up to 200. It took him a month. And later, it's something that not many people know. From P of 201 to P of 300, an Indian mathematician, Hansraj Gupta, actually extended this table. And this was also a very important achievement because that helped Sarvadaman Chawla, another legendary Indian mathematician, to find one small error in a statement of Ramanujan on some congruence of partitions, which were later corrected. Anyway, now comes a very important thing. McMahon arranged the values of P of n in groups of 5. So let me show you the picture itself. I hope this is visible. So he has all these values written from 1 to 200. You see these P of n values. So what he did was, when he wrote it, here P of 0 as 1 is missing. So he wrote 0, 1, 2, 3, 4, then put a dash. Then 5, 6, 7, 8, 9, then put a dash. And so on. 5 values, starting from 0, which you don't see here. Now, can one spot something peculiar about the number just before that line? So here I'm drawing a line. Before that, there is a 4. Then I'm drawing a line. Before that, there is a 9. If you look at the P of 4 or P of 9 or P of 14 or P of 19, is there something specific that one knows? Of course, one can guess that these are numbers which are divisible by 5. See here, P of 24, that is also something which is divisible by 5. P of 29, again divisible by 5. So, what's so great about this? Ramanujan, of course, did not stop there. He also looked at what happens if you have P of 5, that is 7, P of 12, that is 77, P of 19, that is 490, P of 26, that is 2436. What do you see about all these numbers? These are divisible by 7. And not only that, again Ramanujan looked at 6, P of 6 is 11, then P of 17 is 297. 297 is divisible by 11. One can actually check that. Then P of 28. This number is again divisible by 11. So, one may say that from there, Ramanujan actually wrote these 3 expressions. P of 5n plus 4 is congruent to 0 mod 5, which simply means that 5 divides P of 5n plus 4, as we just saw. If you take arithmetic progression, 5n plus 4, the partition values are multiples of 5. This and the other 2 things which you just observed. Now you may say, what's so great about this? We could also see it now. But you see, something like this was very, very non-trivial to guess. There are 2 reasons for that. One thing is, partition is an additive process. And here you are talking about multiplicative property of partitions. So that was something which people did not even think about before. See, there was this list made by McMahon. He himself did not spot that. He sent it to Hardy. Hardy also did not spot it. Then Hardy sent it to Ramanujan, and Ramanujan spotted here. And it wasn't because just that line was put before these numbers 4, 9, 14, and 19 that he observed. There was no line before 5 or 12 or 19. 5, 12, or 19. There was no line before 6, 17, or 28, and so on. So still Ramanujan could spot this very important property, which actually revolutionized this subject. Because this was something which Ramanujan did in 1919, just a year before his death. And to this day, people actually work on finding different congruences for partition functions with different restrictions put on them. Why is this important? Because if you are studying certain object whose coefficients of power series expansion turn out to be rich in congruences, then that suggests that that particular expression is something very, very important, because it may be holding some very important place in number theory because of its arithmetic properties. So that is what people actually do even now. 100 years have passed, still people actually get various different partition functions and they study congruences on it. And this is something really very useful. But Ramanujan did not stop there itself. Now, you see, he had proof of this in his lost notebook, you can see. Here also, he proved it. This one, he said he had a proof, but we don't know whether he had a complete proof. Now, people have it. But as far as these 2 things are concerned, how does one approach this? Maybe some kind of elementary properties that we know of congruences to prove these things, observing the generating function also. Another thing is through modular forms, but that is something that I'm not going to talk about. But that would prove the congruences. Ramanujan went far beyond that. What he proved was called by Hardy as the most beautiful identity of Ramanujan, according to him. And what is it? He actually found out a generating function for P of 5n plus 4. Now see the difference. We are not talking about a generating function of P of n that we have already seen due to Euler. For P of 5n plus 4 times q to the power n, and I'm summing n equal to 0 to infinity. What does that give me? Ramanujan gave this answer. It is 5 times something. Of course, then this thing is a trivial consequence of this result. He also proved this by showing that the generating function of P of 7n plus 5, q to the power n, is 7 times something plus 49 times something. So again, this is congruent to 0 mod 7. For 11 also, there exists such a thing, but that has been pretty recently obtained. And it's a very fairly complicated thing. Many things, but everywhere you have multiples of 11 before the infinite products, so that you get this congruence all at once. Anyway, so Ramanujan said that it appears that there are no equally simple properties for any moduli involving primes other than these three. What does he mean by that? So he's talking about primes 5, 7, and 11. These are the moduli. And equally simple properties, meaning why is this, and this considered to be simple property? Because this modulus is appearing as the modulus of the arithmetic progression 5n plus 4 as well. This 7 is again appearing here. This 11 is appearing again here. That's what he means by simple. Now he says that there are no other congruences with equally simple properties. That was something which he stated in 1919, and it was proved only in 2003 that indeed there are no further congruences of this sort. Now, this came up in a very prestigious journal called Inventiones Mathematicae by Scott Algren and Matthew Boylan. Again, in a very, very prestigious journal, Annals of Mathematics, Ken Ono, whom many of you may know, a very famous mathematician, he actually showed in 2000 that if you allow for this modulus to be different than the modulus in the arithmetic progression, so A may not be the same as L, then for all primes L greater than or equal to 5, there are infinitely many congruences. But if your A must be equal to L, then for L greater than or equal to 5, or for any prime L, only 5, 7, and 11 will give you such congruences, which is what Ramanujan did. Anyway, so let us actually now try to delve deeper into these congruences. So we have P of 5n plus 4 congruent to 0 mod 5. What does that tell us? Okay, if I look at a number of the form 5n plus 4, I calculate the number of partitions of that. That will be a multiple of 5. Can I say more? In that, how do these partitions get distributed according to the residue classes mod 5? So let me precisely state that Freeman Dyson actually asked this question in that paper that he wrote in 1944 as a 16-year-old student. Is there any statistic which gives us information about partitions of 5n plus 4 being distributed in 5 equinumerous classes? Now, do I know that it is into equinumerous classes? Well, he actually worked out a few cases by putting n equal to 1, or sorry, n equal to 0, n equal to 1, n equal to 2, n equal to 3, and calculated P of those values and saw that, okay, according to the residue classes, you can actually see equinumerous classes for distribution of these prime partitions, provided you define some statistic. And that statistic he called as rank. And that rank he defined as largest part minus the number of parts. Now, that actually distributes the partitions not only of P of 5n plus 4, not only the partitions of 5n plus 4, sorry, this P should not be there. It not only distributes the partitions of 5n plus 4 or 7 into 5 equinumerous classes, but partitions of 7n plus 5 also into 7 equinumerous classes. Why is that? Let us actually take a simple example. So rank, okay, here is my connection to pi. Okay. So in this area of mathematics, a partition is always denoted by pi. So that has nothing to do with the pi as a number that we are so very fond of. But pi, people actually were so fond of pi that they also started using pi as a notation for denoting a partition of a particular number. So I have a partition of, say, number n. What is its rank? Rank of pi is defined as the largest part of pi minus the number of parts of pi. So let us actually take a particular n, 5. I know there are 7 partitions of 5. I did it on the first slide. Let us calculate the ranks of each of these partitions. So rank is largest part minus the number of parts. My largest part is 5. My number of parts are 1, just 5 itself. So the rank will be 5 minus 1. This is 4. My largest part is 1. The number of parts is 2. So 4 minus 2, which is 2. As simple as that. See here, the last one, I have largest part is 1. Number of parts is 5. So it's 1 minus 5 equal to minus 4. Now you look at all these numbers and look at the modulo 7. So 4, of course, is 4 mod 7. 2 is 2. 1 is 1. 0 is 0. Minus 1 is 6 mod 7. Minus 2 is 5 mod 7. Minus 4 is 3 mod 7. Now when I look at these numbers, every representative of a residue class modulo 7 is present here. 0, 1, 2, 3, 4, 5, 6. That's what we mean by distributing partitions of 5n plus 4 into 5 equinumerous classes, or partitions of numbers of the form 7n plus 5 into 7 equinumerous classes. And this particular statistic, rank, does that job. He made a following conjecture also back then. What is this denoting? This is saying that, okay, the number of, the number of partitions of 7n plus 5, which is congruent to 0 mod 7, is the same as the number of partitions of 7n plus 5, which are congruent to 1 mod 7, is same as up to 6, 7, 7n plus 5. Exactly what we did here for a particular value 5 has to be proved in general, right? If we are saying that this rank distributes partitions of 7n plus 5 into 7 equinumerous classes, we have to do it in general, not for a particular example. And that's what he made as a conjecture in his paper. He also did it for 5n plus 4. Like he said that, okay, the number of partitions of 5n plus 4, which is congruent to 0 mod 5, is the same as for 1 mod 5, 2 mod 5, so on up to 4 mod 5. These were proved only 10 years later by 2 mathematicians, Atkin and 𝕤𝕤𝕤𝕤. But before that, let me say that Dyson actually did the same thing with partition of 6, the 11 partitions of 6 that we have, and he did calculate the rank of each of them. And then we did not see all residue classes. One can actually try this as an exercise. You will see not all representatives of residue classes modulo 11 coming only once there. Some of them do not appear at all. Some of them come more than once. So there is no equidistribution for partitions of 11 and plus 6. And then he said, maybe there exists some other statistic which he termed as crank, which does that job. Okay. In the meantime, as I said, Atkin and 𝕤𝕤𝕤𝕤 proved the 2 conjectures on the previous slide involving modulus 5 and 7. But what about this hypothesized quantity crank? Dyson said that this is perhaps the only instance where something has been defined even before it has been shown to be in existence. After 44 years, so in 1988, Andrews and Garvan was a PhD student of George Andrews, they managed to really get the crank. Initially, in his PhD thesis, Garvan actually got it for vector partitions, which I'm not going to define. But actually, for a usual partition, they were able to find crank together. And there is a very interesting story behind this that many of you may not be knowing. So there was a conference in 1987 marking 100th birth anniversary of Ramanujan. See this year when this crank was found. Of course, this is when the paper appeared. But when was it discovered? It was discovered right in that particular conference in 1987 at University of Illinois at Urbana-Champaign. It so happened that after the conference ended, both of them were going to fly back to their respective places the next day. And so they went to their hotel rooms, which were nearby in the same building. And they decided to look for this crank thing. And by the night, they had that crank. I mean, of course, they may have been working on this since quite some time, but they really found the actual crank, the thing that Dyson asked 44 years ago on that particular day of the conference, that the conference ended. And it is so remarkable that this important discovery was made during the 100th birth anniversary conference of Ramanujan. Okay, so I'll come back to this in a moment, but let us look at this asymptotic formula that I showed you in the beginning of my talk. As n tends to infinity, this divided by this is equal to 1. That's what this means. Now, is there any way to get the exact formula for P of n? Not an asymptotic formula, but an equality. And Rademacher actually refined some the method of Hardy and Ramanujan in their published paper, and Rademacher was actually able to get an exact formula, which is stunning if you see it here. What does it involve? It involves Bessel function of the second kind, I mean modified Bessel function of the second kind, of the first kind, sorry. And it also involves what is called as a Kloosterman sum. This is Legendre symbol, exponential function here with I, congruence classes. And we are completely surprised. I mean, how in the world can this complicated expression equal something which is very simple, which we can just write down very easily? So Professor George Andrews, in one of his videos, which is there on YouTube, in a documentary on Ramanujan, he says that it was this formula that told him that, okay, I'm going into this area. I mean, he made up his mind after seeing this formula that I'm going to go into partition theory. Because, see, this particular infinite series involving Bessel functions, Kloosterman sums is an integer. First of all, that itself is a fabulous thing. And then it is actually giving you an exact formula, not an asymptotic formula. So right from n equal to 1, you will see the equality of this. And nowadays in computer algebra systems, you can, I mean, this is what is being used at the back end. So nowadays we don't have some special attraction towards how in the world they may have calculated values up to 200, because we can just put n equal to 200 and use the partition function there inbuilt in Mathematica, say, or Maple, and we can get an answer within fraction of a second. But only because we have these systems. They did this same thing 100 years back, so that's really remarkable. Anyway, so now let me come into another aspect, which is I believe is very beautiful. You saw the generating function of partition functions 1 upon this quantity. But what about this quantity itself? Now Euler showed that that is also equal to another infinite series, this time not only from 0 to infinity, but from minus infinity to infinity. And if you look at the coefficients of q to the power an integer, then most of the times those coefficients are 0. When are they non-zero? Only when the exponent is of this form. And when that exponent is of this form, how do the coefficients look like? Minus 1 to the power n. Very simple, either plus or minus 1. This is called as Euler's pentagonal number theorem. Why pentagonal number? Because this is actually a pentagonal number. Okay. Now, is there a combinatorial way of explaining this result? And that was done by Legendre, and that actually is something very beautiful. So in other words, what I'm trying to say is that if I compare the coefficients of q to the power capital N on both sides, then what are those coefficients? Say here I have a of n, and here I have b of n. How do I describe those quantities, those coefficients? So this is what Legendre observed. So before I really show you the result, let me just say that instead of these minuses, if I had pluses everywhere, what was this denoting? Something which we have done at the beginning of this talk. Partitions into distinct parts, right? But now there are minuses everywhere. So if I multiply, say 2 of them, then I'll get a plus sign in between. I mean, like minus q times minus q square will give you a plus sign. But if I take 3 of them, minus q times minus q square times minus q cube, then that is going to give me a minus sign. So when I look at the power series expansion of this right hand side, I'm going to get plus or minus ones. Okay, and that's what you see from here also. So it's kind of partitions into distinct parts only, because you don't have one, you don't have in this particular factor q square or q cube or q raised to 4. In this particular factor, you don't have q raised to 4 or q raised to 6 or q raised to 8. In this particular factor, you don't have q raised to 6, q raised to 9, q raised to 12, and so on, right? So this is something like partitions into distinct parts, but with signs which are not always plus. Okay, so something should be done with respect to the signs. So this is what Legendre did. He actually took the partitions into distinct parts and segregated them into 2 groups. One wherein the number of parts is even, the other in which the number of parts are odd. One of them he called by dE of n, the other one he called by d of n. And then what did he find out? dE of n minus do of n is almost always 0, except when you hit a pentagonal number or a generalized pentagonal number wherein I allow plus sign also, in which case this will be minus 1 to the power r, where r is the one which defines this pentagonal number. So that actually is the arithmetical equivalent of this analytical identity. And once you have arithmetical equivalent of an analytical identity, you may actually ask a question. This can be proved using techniques in analysis. But can I prove this just using combinatorial ideas, some counting of partitions, certain particular sets of partitions in a smarter way? That's what was done by a student of Sylvester, who made many important contributions. So he obtained this combinatorial proof. Note that it's not, this difference is not always 0. If this difference was always 0, then that means the 2 sets of partitions into distinct parts, one containing even number of parts, the other containing odd number of parts, are equinumerous, in which case you would have obtained a bijection. But it's a near bijection, because only in these particular cases the bijection fails. Otherwise, the two are same. So in due to only 8 minutes left, I'm not going to go over the proof, but I'll give you an example of why this particular thing works. So again, let us look at the 7 partitions of 5. What I do is, I look at partitions into distinct parts. So how many of them are into distinct parts? 5, 4 plus 1, 3 plus 2. That's it. So now I look at 2 classes. Partitions into distinct parts only I'm focusing on, but how many of such partitions have even number of parts? Note that this is one partition which has even number of parts. See, the parts themselves could be odd, but the number of such parts should be an even number. So here 2, here also 2. So dE of 5 is 2. Now I look at the other set where I have partition into distinct parts having odd number of parts. There is only one part, so odd number 1. So how many such partitions? 1. So this difference is 1. Why? Because 5 is a pentagonal number. How do you write 5 as a pentagonal number? See, what is a pentagonal number? It's something of this form, right? Now just put n as 2. 2 times 3 into 2 minus 1, which is 5, upon 2, that is 5. So 5 is a pentagonal number. When I have a pentagonal number, the difference would be plus or minus 1. In this particular case, it will be minus 1 to the power 2. And so you have the difference as 1. But if I look at 11 partitions of 6, 6 is not a pentagonal number. So now how many of them are into distinct parts? First of all, 6, 5 plus 1, 3 plus 2 plus 1, and 4 plus 2. So there are 4 such partitions. Now, what does our theorem tell? The theorem tells me that if you don't have a pentagonal number, then these two should be the same. So I have 4 partitions into distinct parts, these 3 and this particular one. How many of them have odd number of parts? This one and this one. So DO of 5 is 2. What is DE of 5? 5 plus 1 and 4 plus 2. Again, 2 such partitions. So both of them are 2, and so the difference is 0, as per what Legendre's arithmetical equivalent tells me. Okay, I'm not going to go over the proof of Franklin's on this, but it's really very interesting proof. People who are interested can actually look in George Andrews's book on theory of partitions. But let me actually, in the remaining few minutes, go over some other stunning contribution of Ramanujan. So let me start with these two identities, but even before that, let me actually say, if you have summation n equal to 0 to infinity, q to the power n, that is something when mod q is less than 1, expressible very simply as 1 upon 1 minus q. That's the geometric series we have also seen in this talk. Even that q to the power n, when we change to q to the power n square, that is something completely non-trivial. It goes into the realms of theta functions. Now, apart from doing q to the power n square, I'm also dividing it by this finite product, 1 minus q square, so on up to 1 minus q to the power n, and then I'm summing. Then this particular sum is equal to this particular infinite product, where I have not explained this notation as of now. A semicolon q sub infinity is nothing but 1 minus q, 1 minus a, 1 minus aq, 1 minus aq square, 1 minus aq cube, and so on. So that's what this means. You have 1 minus q raised to 6, 1 minus q raised to 11, and so on. And here you have 1 minus q raised to 4, 1 minus q raised to 9, 1 minus q raised to 14, and so on. And similarly, this is equal to this. Now, what's so special about this? This was obtained by Ramanujan before going to England, but it was obtained beforehand by an English mathematician called L.J. Rogers, whose work was long forgotten. The work was revived by Ramanujan when he actually was in the library of Cambridge University, in the Trinity College library, and he was going over the older volumes of Proceedings of London Maths Society, and there he really found Rogers' work where these identities were proved. After Ramanujan found these identities, Ramanujan actually did not have a proof of these identities. Neither did Hardy nor McMahon had a proof. In McMahon's famous books on combinatorics called Combinatory Analysis Part 1 and Part 2, you can see this as an exercise, or where he says that these have not yet been proved. But later Ramanujan found these proved in much before by Rogers. And what was his first reaction upon seeing this? He was completely overjoyed, elated, and he ran taking that volume to Hardy's office and showed that, see, these identities are proved, these are true. What would be our reaction? Probably, at least my reaction would be, I would feel very disappointed. Oh, somebody already did what I was thinking was my contribution. But see, that's the greatness of Ramanujan. He was so modest, he had done so much, and he really was very joyous of the result itself. Not who discovered, despite of discovering thousands of results himself. Anyway, so there are combinatorial interpretations of these identities. Look at partitions into, let's first again, look at Euler's result. What is it saying? partitions into odd parts, the number of those partitions is the same as the number of partitions into distinct parts. Now, when I have this terminology, distinct parts, what does it mean? Non-repeating parts. When can a part be non-repeating? When the difference between the parts appearing in the partitions is at least 1, isn't it? Now, what if I change that 1 to 2? That's exactly what comes into the combinatorial interpretation of this. The number of partitions of a positive integer into parts which differ by at least 2. So this is the subset of partitions into distinct parts, right? Because partitions into distinct parts are partitions into parts whose difference is at least 1. Now I'm asking for difference at least 2. So it's a subset of that. Those partitions, if I take, that number is the same as number of partitions of that particular integer into parts which are congruent to 1 or 4 mod 5. So it's slightly more involved. And with respect to proof, of course, it's quite a lot involved. It's none of the proofs of these Rogers-Ramanujan identities is simple. Okay, all of them are quite involved. In the second one, the other description is that you have partitions again which differ by at least 2, but you also are not allowing 1 to be a part. That's what the left-hand side actually is describing. So say I take this left-hand side, I expand it as a power series. What is the coefficient saying? Coefficient is giving this number of partitions into parts which differ by at least 2 and with no ones. And what is that equal to? On the right-hand side, the number of partitions of that integer into parts which are congruent to 2 or 3 modulo 5. So these can also be proved combinatorially, analytically, but these are very difficult to prove identities. Okay, now I hope if it is okay if I go ahead, go extra by 2-3 minutes, I'll just wrap up.
Sure, sir.
Okay, thank you. So let me actually describe what is called as Rogers-Ramanujan continued fraction. But before that, let me talk about this continued fraction, which I'm sure most of us have encountered in junior college or during our bachelor's, and we were very quick in getting this answer, 1 plus root 5 upon 2. So first of all, for those who don't know about continued fractions, it's a fraction which never stops. Okay, so it's 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus so on. This notation is so that I can write it compactly. And let me tell you one funny thing which Professor Brisbane told me when I was his PhD student. He said that he had written Ramanujan's notebooks volume 3. He had sent it for proofreading, and that had lot of pages on continued fractions, and he had used this notation. And the copy editors thought that, okay, he has done mistake, this plus should be here. And he changed all these pluses, which are down, to here in the center. Now, first of all, if you put this in the center, will this even converge? It will be 1 plus 1 plus 1 plus 1, so on. This will be infinity. So he said that I had to again redo all of those things. So he was not happy with the copy editor. Anyway, this is the notation for continued fraction: 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus. So because this goes on forever, how do we prove something like this? We can say that, okay, let this be equal to x. Then we take 1 upon x. That will be 1 plus, again the same thing. So 1 upon x is 1 plus x. So we solve for the quadratic. Because this is a positive quantity, this gives us the answer 1 plus root 5 upon 2, one of the two roots. As simple as that. Only when I can say that this actually converges. But of course, in junior college, we were not conversant with convergence. So we used to do this all the time. Now, what Ramanujan did, Rogers-Ramanujan continued fraction. Even Rogers did, but Ramanujan went far, far beyond what Rogers had done. So he actually looked at this particular continued fraction. You put q equal to 1, you see this is this one. Although it's a limiting case because your mod q is strictly less than 1. Anyway, what is this funny number q to the 1 by 5 doing here? That is just put here so that in modularity, modular properties of R of q are nice. So what Rogers-Ramanujan continued fraction is this particular continued fraction, wherein now instead of these ones, you have this q, q square, q cube, so on. So it's a generalization of this. And what is it given by? It's given by this infinite product. Anyway, Ramanujan evaluated these at certain specific values of q. And regarding these, Hardy said, these were in his first letter to Hardy. Ramanujan wrote these in first letter, and Hardy said, these formulas defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, nobody would have had the imagination to invent them. So where are these Rogers-Ramanujan identities useful? In Lie algebras, statistical mechanics. Actually, I had some slides about statistical mechanics, but I will not go into that. Partition theory, of course, modular forms. Algebraic geometry, K-theory, conformal field theory, group theory, Kac-Moody, Virasoro, vertex, double affine Hecke algebras, knot theory, orthogonal polynomials, probability. So many areas. Because this is very fundamental. Transcendental number theory. Anyway, this statistical mechanics part, let me skip and I'll just go ahead with concluding remarks. So we have only seen the rudiments of this beautiful area of mathematics, in particular of number theory. And here is a quote of Sylvester. He said, partitions constitute the sphere in which analysis lives, moves, and has its being, its existence. And no power of language can exaggerate or paint too forcibly the importance of this till recently almost neglected, but vast, subtle, and universally permeating element of algebraical thought and expression. See, till the time of Sylvester, this particular area was not that much worked upon. But of course, after that, all these people, Sylvester himself, Hardy, Ramanujan, George Andrews, Bruce Blount, and Frank Garvin, all these people, Ken Ono, they have made so many advances that this is now a very famous area and very important area. With that, I will stop. Thank you.
Thank you. Thank you so much for the wonderful talk, sir. It was truly reflecting, and I can sense a fragrance of wisdom and knowledge in here. It was very nice, sir. And I'm moving to the interactive session, which we were all expecting. Yeah, we can see the reactions, the happy audience. And also, I should really mention, we were having 200 plus audience till the last 5 minutes. And it's amazing.
Thank you.
So now everybody can unmute and everybody can switch on their video. So those who are asking questions, first please introduce themselves and then ask your question. So I think let's start the interactive session. Sir, is it all okay? Yeah, thank you.
Yeah, of course.
Sir, myself, Tapan Kumar Mudli. I am a PhD scholar from VNIT Nagpur.
Okay.
Sir, how it is helpful in Lie algebra? How it is useful in Lie algebra?
So in Lie algebras, you have these identities, the Rogers-Ramanujan identities. They come up as in the study of these double affine Hecke algebras, or Virasoro algebras, or things like that. So even now, for example, there are some mathematicians. I mean, Jim Lepowski from Rutgers University is a very well-known figure who uses all the time Lie algebraic techniques and has partition theory and Q-series identities almost always coming into his research. His students, Shashank Kanade and Matthew Russell, or Caparelli, previous student, they also had made stunning advances. Because I don't work myself in Lie algebras, I don't know exactly how, because I don't have Lie theoretic background to tell you about it. But these type of identities of Rogers-Ramanujan type always come in those areas. So many students are asking for slides, so I'll share them with Dr. Vinod Kumar and Dr. Bijumon R, and then you can distribute them.
Thank you, sir. We can share it with the recording of the program.
Yeah, good evening, sir.
Mm-hmm. Good evening.
I am Dharmendra Singh from BRC Visakhapatnam and from nearby Agra. I want to ask how can we do come into this field introductory books.
Okay, so so there are two books. One of them is by George Andrews, and it's like the Bible of
Yes.
partition theory. It's called Theory of Partitions. Before that, if somebody even wants to have even more introduction to this area, then there is a book by again George Andrews and 𝕻𝕒𝕥𝕚𝕛. It's called Integer Partitions. It's a very, very interesting book. I mean, anybody right from school days can actually start with it. And after one is well versed with that, can go into Andrews's book. Andrews's book is a standard book containing great introduction to this area, but it might be requiring the convergence aspects of infinite series or infinite products to be known beforehand. For the other one with George Andrews and 𝕻𝕒𝕥𝕚𝕛 together, you can just start reading that. So, and then there is another book by Bruce Bundt called Number Theory in the Spirit of Ramanujan. That's also a very good book to start off with. I hope that
Yes, sir.
answers
Thanks,
your
sir.
question. Yeah, okay.
Audience may please utilize this opportunity. You can ask your questions as fast as possible.
So somebody is asking about why today we celebrate Pi Day. There is a simple answer is that
I know
14th
the answer.
in US or in many Western nations, they write first day. I mean, in India, we write it day and then month. In US and other nations, they write month and then day. So it's 3/14. So it becomes Pi Day, 3.14. But in Indian calendar or the way we write, we can also there are also other things which are celebrated, like Pi Approximation Day, which is 22nd of July.
July.
22/7. But that according to our calendar.
All interesting facts.
Excuse me, sir.
And also, I like to mention again that those who are asking some questions, please turn on their video and introduce yourself, and then please ask your question.
Excuse me, sir.
Sure.
This is Malay. Good evening, sir.
Good evening.
Sir, I have one question. No, the film is made by the Srinivas Ramanujan, and that. So the film name they given the Who Knew the Infinity, the Man Knew Infinity. So why this title, sir?
Oh, the Man Who Knew Infinity. That's actually a very good question. It's a kind of philosophical question also. So when you actually say that somebody has this touch of infinity or one who has experienced infinity, when do you say that? When somebody is actually so well versed or familiar with that particular subject that it's like he knows everything about that subject. And if you look at Ramanujan's contributions in these areas, he made stunning advances in so many different fields. He started these many fields of mathematics also, like for example, these Mach theta functions. Mach modular forms is a hot topic in mathematics, hot area of mathematics, which is started from Ramanujan, right? How does somebody who merely lived for 32 years could do so much, could actually get so many branches started? It requires a touch of infinity for that. So I guess this title, which is for the biography of Ramanujan by Robert Kanigel, this was first used there, The Man Who Knew Infinity. This was very apt. And yet, Ramanujan always used to say that goddess Namagiri actually shows these things to him in his dreams. So he was very modest. I mean, that's also very natural, right? To say that this is not my contribution, but this is contribution coming from God or from infinity or outside of our capabilities. But he was very modest, so that's the reason why he said that. Yeah.
Hello.
Okay, sir. Thank you.
Very
Hello.
good evening, sir.
Yeah.
Sir, it a very fruitful session, and I really enjoyed your lecture. So, sir, one of your slide, I have seen application of partition theory. So, I wanted to know and very eager to know that what's the application in the field of statistics and probability? How one can use this partition theory in that field?
So if I look at, say, partition values P of n, one very basic question that one gets is that when is it an odd number? When is it an even number? P of n, right? So a very famous conjecture which was solved recently was half the time it takes odd values, half the time it takes even values.
Oh,
It's not very obvious, right? It may be biased towards odd values or biased towards even values, but that doesn't happen. So something like that is what is the basics in probability, right? I mean, we say, I mean, what is the probability that something is odd? Or what is the... So in this way, this has connections. There are also, of course, I mean, this is something I just thought off the top of my head. But I don't know exactly in because I don't work in the area how partitions come into use. But you see, something similar to how omega of n is in number theory the number of prime factors of an integer n. Okay, so this particular thing has a normal distribution, is what is a very fundamental theorem in probabilistic number theory, and that is due to Hardy and Ramanujan, and that actually started this area of probabilistic number theory. So using number theoretic tools in probability or probabilistic tools in number theory, that is what this area is meant to be. Now, similar to omega of n, you can ask similar questions for P of n, because omega of n is just one sequence. You can also do similar things with P of n. And that's where probability and number theory has its confluence.
Okay, thank you, sir.
Sure.
yeah. If you take any number at random, will you be able to tell whether the number of partitions is odd or not? What is the probability that it's going to be odd or even? Probabilistic number theory is also due to Paul Ehrlich, who did a lot of work on probabilistic number theory.
Right, right.
Hello. Good evening,
Hi.
sir. Sir, first of all, I would like to thank for such an interesting talk. And I was just wondering that I have seen that movie, The Man Who Knew Infinity, but there is still a lot of things like there are lost notebooks, and there is very interesting story about how they found those lost notebooks.
Yeah.
Like Andrew Sir went to some library and then they
Yes.
took and some mock data films. And so I was just wondering, can we see part 2 of this picture in the coming years?
Part 2 of the picture. That's a
movie, you mean?
Oh yeah, we would all love to see that.
I was just wondering, sir. I thought that there is a lot of interesting stories still missing.
Perhaps we should tell Professors Bruce Byrne, George Andrews to make such a movie, because these are living legends and who have played role in this lost notebook, and it would be really fabulous to have such a thing. I mean, yeah, it's a good suggestion. In one of my events to Bruce Byrne, I'll try to tell that you were requesting that. Yeah.
Thank you, sir. Thank you very much.
The participants may know that the book by Robert Cannibal has been translated to 7 Indian languages, including Bengali, Malayalam, Tamil, Oriya, Gujarati, and one more, Marathi.
Right. And another interesting thing which was recently done, and that is for kids. I mean, I'm really talking about kids. George Andrews' daughter has written a book, The Boy Who Dreamed of Infinity. It's a book with pictures. I mean, it's a story of Ramanujan, but for kids. Like my daughter actually just read it. Like she's 7 years old. So
Fine.
it is useful for somebody to initiate the story of Ramanujan at a young age to your kids.
So yeah, there'll be more fans for him, youngsters.
Yeah.
Good evening, sir.
Sir, can you repeat that name? That's what is it?
The boy who dreamed of infinity.
Okay, sir. Fine.
Yeah. Hello.
Yeah. Good evening, sir. I am Shikha from Birla Institute of Technology, Mesra. I'm a second year MSc student. So your session was really very impactful, and even for beginners, it was very nice. We can connect to it because you have added few clips from the man who knew infinity. It was really very interesting, and we can connect to it, and we get to know a lot new concepts, and it was very interesting overall.
Thank you. Thank you. Thanks a lot. So, Dr. Vinod Kumar, I'll have to leave in a few minutes.
Yeah, okay,
Yes,
so
yes.
we can wind up within 1 or 2 minutes with
Okay,
a
sure.
couple of things.
Yeah,
Arjuna,
I mean, the only reason being I have to drop some guests at Ahmedabad railway station, which is why I so,
okay, sir. Within 5 minutes.
sure. Yeah, sure.
Okay, so I am just moving to the official vote of thanks, and I just like to say that I'm really happy to see Unnati and Kajal, who are also in the organizing team. We had a very nice promotion video from Unnati. So moving to
Arjuna, 1 or 2 have raised their hands. If time permits, let them ask some questions.
Okay, so if
Okay.
others are okay, I am totally.
Yeah, it's Nishita, you may ask.
Hello.
Yeah, hi Nishita.
Hello, sir. I'm Nishita Pandharkar from TYBSc Mathematics student. I'm from Maharashtra.
Okay.
Sir, today's lecture was very amazing, and
Thank you.
I observed the way when you were teaching us some identities, you were also telling about that incident of Ramanujan and your excitement at that moment. I just enjoyed all the things a lot.
Thank you so
And
much.
thank you so much for this wonderful session. And I'm also thankful to Vinod Kumar sir. And happy International Mathematics Day.
Same to you.
Thank you.
Thanks for the comments. Yeah.
So,
Hello.
sir, shall I proceed to?
Yes, Arjuna. Yes.
Okay, so I hope everybody here is so happy, and it is a well-spent Pi Day. So moving to the official vote of thanks, I would like to welcome Gayatri. Hi, Gayatri. Your audience okay?
Yeah. Hello. First of all, I'm really grateful and delighted to get an opportunity to deliver a vote of thanks on this webinar. And a very big thanks to our resource person, Dr. Adul Dikshit sir, who gave an incredible talk on the topic, the theory of partitions. And it was really a wonderful session. And you have shared a lot of new important informations with us. And you have talked about the great contributions of Srinivasa Ramanujan and other great mathematicians. Thank you so much from the bottom of my heart. And special thanks to Dr. Vijay Kumar sir, who have given an introduction to our resource person. And I would like to thank the entire organizing team, especially Dr. Vinod Kumar sir, Associate Professor, TMG College, Tirur, Kerala, the backbone of our team Maths Aspirants. And I'm really thankful to him for organizing these kind of amazing webinars. And thanks to Dr. Bijumon sir, Associate Professor, MG College, Iritty, Kerala, for providing continuous technical support all the time. And I also want to express my gratitude to Ms. Gia Ross Johnson, Research Fellow, IIT IIT Madras, and Ms. Anne-Marie Tony, Research Fellow, who sat Kerala, and Ms. Kajal Sachdeva, Research Fellow, MD University, Rohtak, Haryana, and Ms. Unnati Shukla, MTech student, IIT Dhanbad, and our host, Ms. Ajana, for their amazing coordination throughout the webinar. And finally, thanks to all the participants for helping us to make this a huge success. And thanks to each and every one of you. Thank you.
Thank you.